Good evening, everyone. Aniketh here, and today we are going to talk a little bit about BKD, how it looks in the file format, and some of the work that I did along with Guo Feng and Adrian Grand on how it encodes doc IDs. Okay, so disclaimer first, my slides don't look as good as the other presentations so you're seeing, but hopefully the content makes for it. A little bit about myself. So I'm a developer who recently started working on the search area on OpenSearch, and as I work on the search area, I also, since OpenSearch is distributed Lucene, I got to use Lucene a lot and interacted with some of the components, especially BKD. Okay, so oops, looks like the slide is not fitting, but never mind. So the agenda for today is we'll start with basics of what a KD tree is. How does the file format for a BKD look like, the KDM, the KDI, and the KDD, what do these things mean? A little bit about the points API and how does the indexing happen. Then what are the differences between the indexing when it is happening for one-dimensional points and when it is happening for two-dimensional or more than two-dimension points. Then how does a KDI node look? What are amazing set of optimizations that the Lucene folks have done to reduce the size as much as they can. And then we are going to go to the main part of the talk, which is doc ID encoding schemes. The various encoding schemes that KDD uses, and then we are going to look at a little bit of how what are the different ways where you can basically do integer sequence compression. And yeah, we'll conclude the talk by looking at some assembly code generated from Java. Okay, so to start with, what is a KD tree, right? Like, why do we even need a KD tree? So let's assume that if you have points in a two-dimensional points, X and Y, right? Why can't you just sort them first by X, then by Y, and just simply create a binary search tree by lexicographically sorting them? The reason that KD tree is so good than just a lexicographically sorted binary search tree is that at each level, you can certainly exclude one subtree based on that dimension, whereas in a binary search tree, if you lexicographically sort it, you would always have to know the X. So if you do partial searches that just contain the Y, you cannot, you will basically have to end up traversing the entire tree. So in this particular case, the entire set of points, which is A to P, is so first split is done on the X value on A, and then the red lines, the red lines are split on B and C, which is on the Y axis, and then it keeps recursively going. And then the tree, the nodes in the tree equivalently represent which parts were split on, and yeah, the leaves basically are the leaves. So this is generally how a KD tree looks like, and the BKD is an advanced version of this KD tree, wherein it doesn't store the entire value on the nodes, but yeah, we'll all come to that. But yeah, so this was just giving a brief introduction of what KD tree is. Okay, so the data structure that we are going to be looking at today is essentially a part of points. So whenever you have a Lucene field wherein you're storing, let's say, integer, long, float, so those get encoded, the index gets encoded as a BKD tree, and then whenever you do range queries on them, range queries or even a term query, like it goes and tries to use the BKD. And then it is also used in geopoints, which I'm not going to cover today. There are triangles, shapes, and stuff, which is something I have to wrap my head around still. But yeah, okay. So now the time for a review. So this is roughly how a BKD tree today looks like in Lucene. So, okay, some of the interesting facts about this BKD tree So the things at the bottom that you see numbered from 1 to 16 actually contain the data. So let's say if you have a two-dimensional point, the points, the entire value of the point won't be stored in the nodes, right? So this is like one of the optimizations that Lucene does. And the next thing is, none of the so the nodes that are colored yellow are the left nodes, and the orangish ones are the right nodes and the root node. There are no left nodes on the last level. That's why you can see just the green ones, the right nodes. So, and none of the left nodes store any file pointers at all. So it's not like a typical tree where each node is storing pointers to the left and right. So, and the numbers that you see over here, 1, 5. So what these mean is that every root node and every right node is pointing to its leftmost child. So A is pointing to the leaf block 1. Similarly, I is pointing to 3, E is pointing to 5, and so on. And the last level, the green nodes, the leaf right nodes, are pointing to the block that they are supposed to point to. And on top of this, each of the nodes store the delta of the file pointers. They don't store the entire file pointers. So that's why, like, one of the first things I had done was just index 2 billion documents into a BKD, and I just indexed from 1 to 2 billion literally. So it was like a bit of an artificial data, but my mind was blown when the index size was less than 10 MB. So the entire KDI size. So this part which you see, the KDI, not the KDD. The KDI was less than 10 MB, and I was like, how is this possible? Which led to explore these optimizations like file pointer delta encoding, and not storing the values and only storing the split dimension. So if you have like a 3-dimensional data, it won't store all the 3 dimensions in all the nodes. It will just store the dimension that it's split on, and it will also, so okay, let's say at A you split on dimension X, then you split on dimension Y at B and C, then you split on dimension Z on D, E, F, G, then you again split on X on H, I, all the way till O. So the node H, I, these guys will store the common prefix, will not store the common prefix, will just store the suffix from the previous split dimension. So that's like a lovely optimization which like reduces the size a lot. Okay, so I was supposed to like put this slide later, but a bunch of my folks said, yeah, this should like first get the picture in everyone's head so that we can continue a bit ahead. Okay, so in a Lucene index which contains multiple segments, so this is like how a segment will look like. Each segment will have KDM, which is the metadata about the BKD. Things like what is the minimum point, what is the maximum point, how many unique docs are there. We'll come to it in the next slide. Then there would be the KDI, the tree that you just saw, and followed by the KDD, each having their header and footer, which will have some magic values, just for Lucene to verify that the segment was not corrupted. Okay, so what is the KDM contained? So Lucene has an internal field ID for every field. It's the field class dot number, which basically tells you the internal ID. So that is the first thing that is put there. A BKD has, you can store dimensions in a BKD and then choose to not index all of the dimensions. So some of the dimensions will be stored and some will be indexed. So today the limit is like you can store 16 dimensions, and at max you can index just 8 dimensions. Then there will be bytes per dimension, which is something like if you're storing an integer, let's say X and Y integer, so there will be like 4 bytes per dimension. If you're storing long 8, that information is encoded. You cannot have varying, you cannot have dimension with varying bytes within a single value. So like each value should have a fixed bytes per dimension. And then there is points per leaf. So points per leaf basically means how many values would each of these leaf blocks contain. So typically the default is 512, and if you want to change the default, you will have to override with your own codec, which Lucene experts do and very few regular users would. Then you would have min and max points in a segment. This is very crucial. Like in OpenSearch as well as in Elastic, and anyone who uses Lucene or is a downstream consumer of Lucene, this min and max point is very effective to skip a segment. So let's assume I have a range query which is going over last 10 years of data, and I just want to not even go and read this segment. So I just read the KDM, I look at the min and max. If it's not in the range, I just skip the entire segments. I don't create the scorer and do all those things which Ankit was talking about before. Then we have the unique doc ID count in the segment for a field. I don't completely remember what is this exactly used for, but yeah, I mean it's a metadata that is also kept. And then we have the unique point count. Like this basically means that how many unique values did this particular, how many unique points did this BKD see? And then obviously we have the file pointers to the KDI and the KDD. So this is the first file that gets created, the KDI. Okay, so I'm sorry if I'm going a bit fast, but you can stop me if you have any question. So the next thing that we are going to look at is how does the entire BKD integrate with Lucene's core indexing code, right? So Lucene's core indexing and merge logic essentially treats different type of data structures differently. So points format is the one which basically at a high level gives you an idea of how points can be stored. So if tomorrow you are feeling excited and you want to write your own BKD implementation, this is what you should be extending. But for the one that Mike has written, the classes that go inside are BKD writer and the BKD reader, so basically the Lucene codec expects a points format, and a points format gives you a reader and a writer, and which eventually goes to the BKD code. You have similar things for term vectors, you have similar things for doc values, for KNN vectors, and all the other type of field indices present in Lucene. Okay, so let's, so I'm just going to quickly show you a slide of what happens when you're adding docs to an index writer, specifically this writer.add document. Before you commit, like what does Lucene do internally to store these things? So essentially for every doc that is getting added by the, like for every doc that you're adding, the indexing chain essentially stores it in a 2-dimensional byte array, the doc ID as well as the point, right? And whenever the indexing chain calls a flush, that is when actually the codec comes into the picture. Till then everything is like, there is no optimizations going on yet. So then this so now this is where a bit of nice good code quality comes into the picture, because this byte array is not passed as a byte array to the BKD writer. It is wrapped in another class called point tree. So the BKD code still looks at it as if it is traversing a tree, but underneath it is a 2-dimensional byte array, right? And then this goes into the BKD writer, which basically takes it and creates all the 3 files that we just looked at before and flushes them. The next 3 slides, I'm sorry, I put a lot of content over there, so it can be a bit overwhelming, but yeah, I hope that it's not too much overwhelming. Okay, so BKD has special, the BKD writer and the entire BKD module in Lucene has special logic to handle 1-dimensional point and 2-dimensional plus point. So that's like 2 splits present inside the BKD module. So for 1-dimensional, what it does is that it sorts all the points based on the value first, right? So let's say you have 1 to 100, like 1 is repeating 5 times. So it will first sort everything by value, and then within each value, it will sort everything by the doc ID, right? So this, it gets this view first, and then the point tree that was given by the, that was given to the BKD writer before. Now it just starts visiting this point tree, and then it starts again buffering them until it reaches the value of 512, which is like how many points can you have in a leaf block, right? So once it reaches this 512, that is where it starts writing the KD. So in the KDD, it will record the file pointer, which will again be a relative pointer based on the size, right? It will record the split value. So in case of one-dimensional, there is no dimension, like there is only one dimension, so it will just record the first value of that block. Then this is where it so now when it is writing these values, it doesn't write them entirely. It calculates the common prefix length. So BKD, the entire BKD code doesn't treat your values as regular Java integers or longs. It treats everything as byte arrays. So your integers get encoded to byte arrays, longs get encoded to byte arrays, and the common prefix is calculated on each byte of these byte arrays rather than treating them as integers, regular integers in the code. So once the common prefix are done, then it will, the doc IDs are encoded and written. How they are encoded and written, we will, there are further slides for those. And then the suffix for each value, the common prefix is just written once, and then the suffix is written for each of the value. And then, yeah, this keeps going on until it goes through all the values. So 1D, there is a radix sort code which is like a common Lucene utility which is used for sorting. I don't have much context on that, but so I have like skipped it out of this slide. Like I've not made it a part of this presentation, so don't ask me questions now. Okay, so yeah, now coming to 2D leaf block generation. So 2D is a bit different, right? So in 1D case, yeah, so one of the very important things here is that, as you would have heard in the previous talks, is Lucene is write once, read many times kind of model, right? Because, so that is why we are optimizing here by, like, we are paying the cost of sorting the data to help us in the search later, right? And by sorting the data, when we group the doc IDs of the same points together, in some cases, it also makes us apply much better encoding schemes than if we would have not sorted. So that's one of the key points that I would like to highlight. Okay. Now coming to the 2D generation, so what in case of 2D generation, it doesn't sort all the data. It basically at the first pass, it goes through all the values and computes the min and max, right? Once it computes the min and max, it again, there is a common prefix computation between, like if it is a 2D, a 3D, or a 4D, 4-dimensional value, it will also compute the common prefix, store the common prefix, then again it uses a variation of radix sort to give it all these values which are not yet sorted, and then partition them on a midpoint. So that the radix sort, it's basically a radix sort selection code which basically partitions the point so that all the points that are less than the mid go to the left, all the points that are right, greater than the mid go to the right, but it is not fully sorted. And then it just recurses on the left and right, it keeps recursing. And another optimization that we had seen before, which was recording the prefix of the split dimension, is also done. So yeah, the min and max is not calculated at every recursion cycle. So it is calculated only at every 4 recursion cycle, which is what is done in case of 2D. Yeah, and when it reaches the last recursion cycle, it again just writes down everything. It writes the KDD, it calculates the cardinality of that leaf block. So it will stop the recursion as soon as it reaches 512 points, and it will write the cardinality, it will write the doc IDs, it will write the common prefix, and it will write the suffix of each value, right? Okay, so I think we are done a bit with the text. So now we have the leaf blocks. So at this point, we have only generated the last KDD, the leaf blocks, and we have not yet generated the tree. So this is again a good coding standard that I saw in BKD's code, was that I think I skipped that. So the 1D code and the 2D code have their own logic of how they generate the leaf block, but then Ignacio Vera, he's also a very major contributor on this BKD module. After Mike came out with the initial implementation, he basically made the contract from the 1D code and the n-dimensional code to come to a common place, give the split dimension and the value at each leaf block, right? The file pointer of each leaf block, and then have a common code generate the tree out of it. So how the tree gets generated, so you have an array of leaf blocks. In this case, there are 5 leaf blocks. We figure out where to partition these leaf blocks. So how many leaf blocks should be on the left, how many should be on the right, which is what is given by the split offset. Whatever you see from the right offset goes on the right subtree, and whatever is on the left of the right offset goes to the left subtree. And the value of the dimension, which is on leaf block 3 in this case, will go to the root node, right? And then it will keep recursing and build the entire tree. So this is where the KDI node gets created. So now let us look a little bit inside of how does a KDI node looks like, right? So as we discussed, firstly, a KDI node is stored in a pre-ordered fashion. So you have your root node, the left subtree, and then the right subtree, and that's how it keeps recursing. A node, so in a KDI node, only the root and the right non-leaf right nodes would store file pointer deltas, which is basically which leaf block do they point to, which would be their leftmost leaf block. Then they will store something called as a code. So this code has a has a slight mathematical formula, which I have not put here, but essentially this code can tell you a split dimension. It's basically a variant which can tell you the split dimension ID, like which dimension was this node split on, what were the common bytes with the last split value, which basically tells you, so that's why like it doesn't store the entire value in each node. So it only stores the common, it only stores the suffix, and the common prefix comes while reading from the parent node, right? So that's what you see in the value suffix. How many bytes were common, and what is the diff for the first byte. So this is another optimization. I won't go too much deep into it, I think, in the interest of time. And then it stores the size of the size of its left child subtree. So when you read a root node, you know that the next node would definitely be the left node, but to go to the right node, you use the size of the left subtree, and then basically move your index input, or like be it a mmapped file, or if it is an NIOFS file, doesn't matter. You basically tell the file channel to directly skip to the right subtree using the size of the left child subtree. And this is how like each of the KDI node gets packed. And moving on to how a KDD looks like. So a KDD has 3 things. It has all the points that fell into the leaf block, right? So you have a bunch of leaf blocks. So you have how many points are there? What doc IDs do those points come in? So the doc IDs that those points come in is basically my core focus of the talk going forward. And the point values are basically the points that were present in those doc IDs. So the points are also encoded using 3 different variations. One is that if you have a unique value across the entire leaf block, which basically means, like, let's say you're storing HTTP status codes, 200. So you would see a lot of 200s. So it would just store the 200 uniquely. It will obviously not repeat it, which is straightforward. But then the next thing it has is low cardinality cases, wherein it will store the cardinality of the point and then the point itself, right? And again, the points are also, they store the common, the Lucene stores the common prefix of the points as well. So that's another optimization which basically reduces the size of the KDD. And then the third kind of optimization is wherein we store the high cardinality with the first byte of the suffix. So this is something that Adrian had proposed some time back, wherein when we are already storing the common prefix, how more can we reduce the size of the KDD? So since the common prefix is all calculated across 512 values, what Adrian suggested that in those 512 values, if we do a run length encoding of the 256 values, right? So if we can, like, if we split it into 256 values and then take the common bytes in them, we can even more reduce the size, which is what this third thing of high cardinality with first byte of suffix does. Okay, so these are some of more encoding techniques that are present in the KDD's file structure. Okay, so now for the remainder of this, so this was like a background of what a BKD looks like. It has metadata, an index, and the doc IDs and the actual values that are present in the tree, right? So now we are mainly going to focus on this part of KDD, which is like what are the different schemes that it uses to store the doc IDs. Okay, so a rough algorithm of how it can select which scheme to apply looks like this. So the decision is, the first thing it checks is, within a leaf block, are the doc IDs strictly sorted, right? This generally happens when you enable an index sort field on an index, so that in that case the doc IDs are sorted. So then it can basically see, oh, the doc IDs are sorted and are in arithmetic progression, so I just need to store the first value, right? And it's specifically arithmetic progression of 1. So it's not like arithmetic progression of 2, 3 or more. Then the next is a delta encoding, wherein it will let's say in a 32-bit integer, it will store the first 16 bits as the common prefix and only the next 16 bits as the suffix. So the common prefix of 16 bits. So basically, essentially, you are representing a 32-bit integer as 16 bits. So that is another optimization. But to do this, oh sorry, I think I missed one of the optimizations. So there is another thing wherein it stores. So this was contributed by Guofeng. So the optimization over here is that it will check the max and min of the doc IDs, right? And if they are within a certain range, which is like 16 into 512, the doc IDs are literally stored as a bit set. So that in Lucene, like every iterator is supposed to, the DCs are like whenever you're running queries, you expect bit sets, right? So if you can directly load a bit set and pass it, the queries become much faster. But these bit sets expand the storage a lot, so there is a limit put on it. And then following this, there are 4 different kinds of optimization. So the first one is what we just talked about, 16-bit delta encoding. Following this is something which, so this is all the things that I'm writing here is specifically contained to one class. So this is where I like, when I was going through BKD's code, whatever you saw before was really, really hard to understand. But the moment I reached this class, I was like, okay, this looks very well contained, right? So this class is basically an answer of how you can do integer sequence compression using various techniques, right? And before there used to be like this 24-bit compression. So basically you would use 24 bits to represent an integer, wherein you are saving like 8 bits per integer, which is again great. And if nothing works, then you can always use 32 bits to store an integer, right? So between the 16-bit delta and the 24 bits, I could see an opportunity wherein, what if you can store 3 21-bit integers in a long, right? And this is where this whole talk started from, and wherein I started the implementation. Okay, so a lot of text. So let's go back to diagrams. So let us say if we use 20 bits to represent an integer and encode them in longs, how would it look like, right? So you would have 20, 20, 24, and then so on and so forth. But I just wanted to show you some interesting thing I saw when I was working on this, was when you see this 12, 20, 20, 12, so every sequence will have a palindromic subsequence which will come, after which the whole pattern repeats. Don't believe me? Let's see for another case. So I basically wrote out a program from BPV16 to BPV32 to see where all this pattern comes. Let's take BPV30. See, 2, 30, 32. And then the whole thing repeats again. So that's a very interesting thing that I saw while working on this encoding schemes. Okay. This was just like a fun trivia that I wanted to share with you.
Is there like a mathematical proof? Like, why is this happening?
I am not sure. Most of my mental energy.
The whole thing is a palindrome, right?
Yeah.
So in the middle, you're guaranteed to have a palindrome.
So when that palindromic subsequence comes, then the whole thing starts repeating again.
Right.
So
That's
like
the center of the palindrome.
Yeah.
I see.
If it's odd, you might have one. There's only one in the middle, right? Yeah.
But why is the whole thing a palindrome?
I
So
don't know, but it is.
Like so after 2:30:32, you see 28:36, which was just before it, and then 24:30:10, which was 10:30:24. So it repeats like that.
It's like seeing shapes of animals in the clouds.
I mean, it's like that. Like if somebody wants to do a mathematical proof, let me know when you will get it. So yeah, this was like an interesting thing. And interestingly enough, the two encoding schemes that we saw before, BPV24 also has this, right? So 24, 24, 16, and you see this palindromic string, and it repeats again, right? So when I was analyzing this, I was like, what is so good about BPV24? So in Lucene, you would find a lot of numbers, block sizes, posting sizes, 128, now they are increasing it to 256. Leaf block size was 1024, now it is 512. So these are like very cryptic numbers, I feel. So for outsiders, like they don't get the context of why, right? Like sometimes there are comments, sometimes you can go back to issues, but sometimes you don't know why, what were the developers thinking. So one of the things that puzzled me was, what is so great about BPV24, right? Why is it is doing such a good encoding? So I just did a bit of in the program where I generated this sequences, I also generated what would be required to decode the values, right? So in this case, to get the first integer, you would have to right shift the 24 and you get the first integer. For the second integer, you will have to mask the 24 bits, right shift it, you get the second integer. For the third integer, you will have to mask the 16 from the first long, then left shift it, then you will have to mask the 8 from the second long, right? And then you will have to OR them both to get the entire 24-bit integer, right? And you keep doing that and you get these instructions. Oh, oops. So these instructions were like, it was somewhere around 1152 operations for a leaf block. And if we calculate the same number of instructions required for all the other BPVs, they will always come to be more than BPV24. So that is another interesting thing, right? And don't ask me why, like, right? So yeah, so I was like, this theoretically makes sense, but computers never follow theory very well. So so yeah, and while doing this, I saw the case for 21 that its repeating pattern would have not fit into this entire projector. So it was like huge, like it does have a repeating pattern, but it comes in very, very, very late. But while seeing that repeating pattern, I thought, like, what if you just store 3 integers in one loss, right? And this is where I opened an issue, PR saying, and Adrian commented, because Adrian and Guo Feng, after Mike and Ignacio have like looked a lot at the BKD module of Lucene. So he commented that, yeah, we use this trick already in other places. Like, oh, great. So yeah, so I was, and if you do instruction counting here, it would be very simple. So you just have to keep one bit unused. So that is what the UB means here. And then you can just, because if you don't keep that unused and you put the 1 there and the 20 there, the pattern becomes very long, right? And the decoding logic takes a lot of time.
I think it's because you have 21 is factored into 2 primes, which are relatively prime compared to 64, which
That's
is
a great
to the
point.
whereas 24 and 64 share many factors.
And
so.
they're all prime, and they're all factors of 8, which is like 8 bytes.
Exactly.
8 bits make a byte, and yeah, that could be, but yeah.
You need 64 longs for it to repeat with 21?
Yeah. No,
So
even
you
more.
need the least common, what's that,
Right.
multiplier
Yeah.
or whatever for it to repeat.
Okay, so yeah, and we if we do an instruction counting here, So for the first 21, you just do a right shift. For the second 21, in the first long, you just do a mask and do a right shift. And for the third one, you just do a mask to get the rightmost 21 bits. And there you have, like, you just need 4 operations to decode 3 doc IDs, which comes to 683 operations for an entire leaf block, right? And you have the space savings here, which is like not too complicated math, so I'm not going to go over that. But yeah, so this is like, I was very happy with this. I implemented it, right, thinking that it would give me great results. And I compare, so my baseline was BPV24, because if we go back to the slides, so if you see the BPV21 neatly sits between the delta 16 encoding and the BPV24 encoding, right? So I had to compete with BPV24 to make it work. And I thought everything will go great, but as things are, they didn't go great. So I was getting different results in x86 architecture, I was getting different results in ARM architecture, right? And I was like, okay, maybe, so I was having a discussion with Michael Fro, and I asked him, Fro, should I just put some things wherein I can just put a conditional logic on the architecture in Lucene code? And he was like, they do have such cases, but should we investigate more? So I was like, okay, I would investigate more. And this is where I was introduced to reading the assembly code generated from the JIT compiler. Okay, so if any one of you is ever interested in going it, so I've just put a brief slide, like what are the different flags that you can use. Obviously, like all these are available, but so I basically started with the JMH benchmark, and I used that JMH benchmark to run it across x86 and the Arch64. And the first thing was to see how much of loop unroll. So basically there were 2 factors here. How much was JIT compiler's auto vectorization coming into the picture, where it was generating SIMD instructions for the code, right? And how much was loop unrolling contributing for the speeder, right? So if you go deep into Lucene's code base, you would see some functions where there is literally hand unrolled loops, basically to help the JIT compiler better, right? And some of the learnings were like, if you disable tiered compilation, so if you don't let the C1 compiler do any counting, the C2 compiler can't do much because it needs the profile data. But if you don't disable, so in the JVM you have like the C1 and the C2 compiler. So the C1 compiler basically profiles your data, like counts how many times this method was called, right, which is a hot method, and using the data from the C1 compiler, the C2 compiler makes decisions as to, should I inline this method, right? Should I generate much more a much more optimized assembly for this method? So one of the keywords, right, use superword. So if you disable this, JIT compiler will stop doing any auto vectorization on your code. So if you use this keyword and run your code, you can be sure that whether your code is getting auto vectorized or not, right? And interestingly enough, we also tested with JDK24's Panama Vector API, which was comparatively worse than the auto vectorization code. Okay. So this is how typical BPV21 scalar implementation looks like, right? So we read along, we decode the 3 doc IDs, we keep moving on, and then there is a remainder loop which catches everything else, right? So this is the scalar implementation that I went with, and this was not performing well and giving there was another implementation where I had unrolled the same loop 3 times, and this hexadecimal number is nothing but the 21 bits from the rightmost side. Yeah, so a little bit going into the assembly of how the assembly for this thing looks like. So the assembly that you see over here is basically essentially just for this line, right? So you can see here it's doing a left shift. These are the register IDs, and this 42 is the 42 for that we have mentioned here. Then this UBFX is basically reading the last 32 bits of of, because we are doing an integer cast here, so that is how the integer cast gets implemented by the JIT compiler, and then all the things that you see below here is essentially assigning to this docker, assigning to an array. So this is all the assembly code that a JIT compiler would generate to just assign to an array. So it is doing bound checking. So this compare is basically doing bound checks and all that stuff. So, oh, I forgot mentioning one thing. So if you ever enable assembly logs, you would also have to place a HSDIS file inside your Java Homes library, right? And how you can figure out where is the assembly for your method is through this last line where you see the org Apache Lucene benchmark decode 21 benchmark. So just above this line is what you will, thankfully, you will also get the line numbers at the end. So you can basically relate this assembly is related to this line. There is also another tool called JITwatch which you can use, but yeah, it generally doesn't do well when you have both the C1 and C2 compilers enabled. So this is what the assembly looks like for, and this is like a continued version of it, where like you have more LSR, move instructions, again a typecast for this particular line, right? Okay, so I was stuck here, didn't know what to do. This is where Guo Feng and Adrian Grant came in, and they said, wait a minute. Instead of taking a look at it as a scalar implementation, what if we force the JIT compiler to do auto-vectorization? And to do the auto-vectorization, this representation kind of changed to this representation, wherein like you have, instead of a long, now you have an integer, like the size and everything remains the same, but you're storing it as 24/8, 24/8, 24/8, right? And one loop would just decode all the 24s together, right? It would be a very simple loop, and that simple loop would look something like this, the first part, right? Okay, yeah, it's that doc IDs, scratch, right shift 11, right? That simple loop would basically decode all the 24s or all the 21 together, and that simple loop tricks the compiler into thinking, this looks very simple, let me just auto-vectorize it, right? And how can we verify that it is auto-vectorizing that? Let's see the machine code. So the machine code or the assembly instruction, if you can see here at the top, it is also doing a left shift, but the interesting part is there are no X named registers, right? Whatever we saw before, there is a Q16. So this is like I think this is a 128-bit register. So this assembly I generated from this Mac.
It's quad, right?
Yeah.
Quad. Yeah.
Yeah. So
it's got 4 integers.
Yeah, 4 integers. It's like a 128-bit register that this has an ARM Neon CPU. So like, yeah. So this is generating SIMD instruction, the LDR, and the second one that you see, USHR, that is also a shift right, but it is a shift right on the SIMD register. It's not a shift right on your regular registers, right? But interestingly, the next part of the code, which is basically, now since we are decoding all the 21 bits together across the entire array, we are left with combining these chunks of 1111 to generate the other integers, right? Which doesn't get auto-vectorized. So that is very interesting because there are a bunch of, so I think we still don't know the exact reason for it. We would have to be JIT compiler developers, I guess, to know the very exact reason for it. But what we speculate is that the more instructions that you put, like the less simpler that you make, the more simpler you make your code, the more chances you have for the JIT compiler to auto-vectorize it. And if you see in the second loop, we have like 2 AND instructions, 1 left shift and 1 OR, which basically, and then there is a doc IDs I plus num ints. So there is an addition as well. So given that there are so many instructions, it's like multiple data, multiple instructions. So you will run scalar. Yeah, so this is where Guo Feng and Adrian Grant essentially came in, and they did this for BPV24, which was in the BPV24 vector pattern that you see instead of the scalar pattern. And they saw my PR, which was languishing. I had also like kind of lost hope there. and Feng took it and he basically implemented the vectorized version, which is what it looks like here, and everything sped up. So it was quite nice, and these are some JMH numbers, and the below, I think the numbers below is something that I took from Mike's benchmarks that is maintained from the Lucene util, so that Feng had raised a particular annotation for this change. And yeah, there were quite some speedups, if you can see from the current and the current vectorized one. So we generated arrays. So the doc ID arrays that we generated were randomized enough.
It's really hard to understand the output because the columns aren't there, but that 0.0000, Mike Sokolov can explain what that is.
Yeah.
That just means it's a significant
Highly
result.
confident result.
Yeah.
0 is good on that
Yeah,
last column.
yeah.
Probability of this result having been generated by a random distribution is 0.
I think everything was not fitting into a slide.
And the 1.2 and 1. I think that's the variance.
Yeah.
Like it runs 20 times. That's the variance of the QPS number. So what you want to compare is 308.2 to 367.7. That's a huge speed up, right? Like 20% speed up on filtered range queries. It's
And
amazing.
Space savings as well.
It's
because
amazing.
21 bits per
You rarely
byte.
get space and speed up.
Yeah, best of both worlds. So, yeah, and another interesting thing we found was, I think I've run out of time, but I guess if there is no other talk, I want to just share this last thing. The last part which Lucene does, right, like the doc ID encodings, which we saw, so the last part, like if it goes through all these filters, none of them apply, it will just store it as 32 bits. So that 32 bits is, we did some experimentation over there as well. So the 32 bits can be written in many ways, like you can write it in a long to 32 bits, you can write it as short, and you can write it as a regular integer, right? And then when we ran, all the three variations are just storing each doc ID as a 32-bit integer. But if you see the numbers, the ones that are storing it as long are the fastest compared to the ones that are storing it as int and the ones storing it as short. So we were very perplexed as to what is happening here. So the index output that is used to write it is behind a memory segment index output, which Uwe had recently migrated to use the memory layout API of Java, right? So each read long call is one call from the JVM to read from that memory. It's like read through that memory mapped file or write to that memory mapped file. Whereas integer is like 2 calls. So it's essentially like the number of calls that you're doing. That's why long is performing the best, short is performing the worst, and int is in between, right? So it fairly makes sense. So instead of using this individual read int and read short, we move to using the batch read ints, wherein you load all the ints at once. So you just make one call to the memory layout, right? There is a read ints variation in present and index input, and yeah, that case. Yeah.
Do you think that in the decode using long, that the JVM is capable of understanding that your packed long can be written into doc IDs in a single instruction? I mean, it can't be done in Java because it wants to make them ints. But I mean, if you were writing C,
Yeah.
you would know that those two ints are right next to each other in memory, and you would just write the long across both of them. Do you know what I'm saying? Like doc ID's I and doc ID's I plus 1 is just one.
It's one
long,
it's one long,
basically, right?
The good old days of unsafe C.
I have no idea what code is being written under the hood there.
I mean, yeah, it's like we'll have to go to the depths of JIT compiler.
Yeah,
but
yeah.
At this point, anyone would say, why are you using Java? If you're going
So
at this,
true.
Yeah. So yeah, I mean, the strange thing is Panama Vector API is not up to speed. So I think hopefully by JDK 25 they do things better and we can deterministically generate SIMD code rather than relying on these tricks. But until then, I mean, like this is all we have for the time being. Yeah. So concluding the talk, I think the paper that inspired BKD, there is a very nice blog by Mike on how like the initial implementation back in 2015-16, I think, and then there is a Lucene committer named Lu Zhugang. I hope I'm pronunciating his name correctly, but forgive me if I'm not. He is basically porting Lucene to Lucene. Lucene is basically the Rust version of Lucene. So while he was doing that, I'm not sure which state it is at now. I think he stopped at 8.6, but he basically created a nice diagrams of BKD, which I was using to start with. Hopefully mine become popular after this. Anyways, just kidding. So this is the initial PR for BPV21, where I proposed the change of storing them as 3 integers as a long, in a long, and then 3 doc IDs in a long. Then along came GoFeng and they did auto vectorization for BPV2416. Then they saw my PR of BPV21, and then they converted that into auto vectorization. And yeah, everything's speeding up since then.
Which Lucene release was it included in?
10.1 or yeah, 10.1 I think. Great. And then so some future area of improvements are whenever Panama Vector API is more stable and it can deterministically generate assembly which is much faster than whatever JIT compiler does in auto vectorization, we can probably port all this code to start using Panama Vector API. And another interesting thing while reading through the entire BKD code that I found out was, oops, I have to go all the way back. So what the traversal today that we do in BKD is we always go to the left node, right? And if our bounds don't match, then we go to the right. So for each level, we are at least reading the left node once, right? So this makes complete sense for 2D, 3D, 4D, and so on. But for the 1D case, we have the real value. So BKD never stores the real value; it just stores the split value at each node, and it kind of pseudo materializes the real value using the KDM. So it takes the min and max value from the KDM and just keeps replacing the bytes for the split value. So it kind of gets an idea of which way I have to traverse, right? But for 1D, that's not the case. So maybe we can do an optimization. I'll give it a try. That for 1D case, don't always read the left. You know what is the bound, so you can deterministically know should I go left or right. The left and then go to right was essential for it to be a common code for all the cases, but probably for 1D case, that decoding of the KDI is not required on the left node.
Is the 1DK specialized at read time today?
No.
Just at write time?
Yeah.
Cool.
So yeah, it's the point values dot intersect which just does the thing. And yeah, so oops, back again. Yeah, and then there are some other things like, so today as we saw that BKD tree is stored pre-ordered root left subtree and then the right subtree. This is great if you are, this is great today because the BKD traversal code always goes to the left subtree first and then it goes to the right. But in case of 1D, maybe there is some optimization if you changed it to a paged layout format, which is much more friendly for the CPU cache. Yeah, and then there are some memory optimizations that I saw wherein the entire KDI, at least for a segment, is materialized as a byte array, which we can probably stream fashion it. So there are maybe some of those areas of improvements. Yeah, so calling for contribution. Oops. Yeah, so like these are the main contributors to the BKD module. Mike did the first implementation, and then came Ignacio. He did a lot of optimizations that we saw with relate to some of the common prefix and the point value ones. Then Adrian Grant also came up with the first byte suffix optimizations. Then GoFeng came and did a lot of things on doc ID encodings. Uwe came and integrated the memory segment API for reading these doc IDs. Robert also did a few contributions on the BKD module. Yeah, and you can be next. So welcome any contributions. Thank you. I went way over time, but
I think there's any risk on the AK upgrades that the hotspot compiler forgets how to vectorize. Our code?
No, I'm gonna take JDK 25 for a spin. Let's see. Hopefully it's good.
Okay.
I think that's why all the Rust and C, C++ based projects are getting a lot of traction.
Yeah, they just write straight to SIMD.
It's
And they can do the long int tricks that Mike was talking about. Just read along into an int array.
And